The next reaction is the addition of phosphonium illid. The pronunciation of this is an illid, and this is known as the Wittig or Wittig. Correct way is saying it the Wittig because it's from German and W means is used as a V. Wittig reaction. We produce what we call phosphonium illids that are adding, this is a very important word here, irreversibly to aldehydes and ketones, but then they undergo a rearrangement in a second step to introduce a CC bond selectively in place of a carbonyl. Basically, what you're doing here is you're making an alkene. You're making an alkene out of a carbonyl. So here's and this only applies to aldehydes and ketones only, by the way. This is for aldehydes and ketones. So this is a ketone. This is the phosphonium illid. The product of this is the following, to make it very simple. What you're doing is you're going to replace this oxygen with whatever is attached on the other end of the phosphorus of the illid. So in this case, the CH2 is going to replace the oxygen. So you're going to make this. Plus, so they switch places. So notice how the oxygen and the CH2 switched places. So what did you produce? You have an alkene. Same thing here. Replace the O with whatever is attached to the phosphorus, So this O will be replaced by this whole thing. Now, we're organic chemists by now. So we're going to need to draw this as an alkene in a nice form. So here's our product. If you were to just take this and put a CH, etc., then it wouldn't show us that this whether this is a cis or trans. So this can become either cis and or trans. Plus PH3PO. Now, before we continue, you're wondering about this pH3, which we will examine in the phosphonium illids underneath. pH is phenyl. And phenyl is nothing but the benzene ring. So imagine this benzene ring is attached. That's the pH 3P. There's a lone pair on it. Before, of course, we're going to see that in the preparation of the illids. So let's examine the phosphonium ylide. So the phosphonium ylide looks like this, as we've shown. pH3P is a double bond with a carbon. Of course, this has a resonance structure, and the resonance structure is those double, the p, well, the pi electrons shift back to the carbon because it's more electronegative. So this has a negative, and now this has a positive charge on it. Now that's what an ylide is. An ylide is simply a molecule, a substance that has two different charges, obviously the positive and a negative, on adjacent atoms, So an ylide is where you have the plus and negative charge on adjacent atoms. Now, of course, they both have the octet, despite, of course, seeing this resonance structure. How do you prepare the ylide? You have to use an SN2 reaction. So we have pH3P. So this is a nucleophile. And we react this with something such as methyl bromide. This is kicked out because this is nucleophilic. And once again, we're producing this. So the Br is out. I'm going to put CH2, but I'm going to show one of the H's. Because that will be deprotonated. Now, this has a pKa of around 35. So it's very basic. So you need something even more basic to deprotonate that. And the only way you can use this is something I worked with in the lab, extremely, extremely basic and dangerous. And that is N-butyl lithium. So that's a butyl group attached to a lithium. So it basically looks like this. So it's an organolithium, extremely basic. This is able to deprotonate that H, therefore producing the ylide. So remember, that's an organolithium. We said organolithium reagents are very basic, very nucleophilic as well. So let's look at the reaction between the phosphonium ylides and the aldehydes and ketones. Now, your book has a mechanism, and I'm just going to follow that mechanism. It's sort of like a concerted mechanism. it's usually, it could be presented slightly differently in other textbooks or maybe in research, but I'm going to use your textbook's mechanism. So what you have is you have, let's say you have a ketone or an aldehyde. This is delta minus. We need those charges are extremely important. And this is delta plus. Oxygen is more electronegative. So what happens is that you align this with the ylide. And it has to be aligned in the following way, and it has to make sense to you. What do you think? How would it align? Would you align the positive to the positive and the negative to the negative, or would you align them oppositely? So the C has a negative charge on it, has a lone pair and a negative. And the phosphorus has a positive charge on it. All right, so the mechanism goes like this. This lone pair attacks that carbon. Yes, you could put it just the usual way, but here it's nice if you align it this way. And then the pi electrons, not the lone pairs, attack the phosphorus. Therefore, you're forming a box now. So it looks like this. So here's the carbonyl carbon, the O. Here's the new bond. CH2. I'm showing them so you can see how it was bonded. P attached to the O, PH3. So this one spontaneously decomposes, and it's going to decompose in a way, again, to produce the alkene, meaning you need this together, this portion together. So the reaction is going to take place this way. So these electrons shift to move and make a double bond between the carbon and the carbonyl carbon, and a double bond between the O and the phosphorus, as you've seen in the products right here. You saw a double bond formed between them. And now you're producing this. There you go. So these are your products. We will discuss the synthesis in class. So take a look at it, see if you can figure out a way of putting together, making this using the Wittig reaction. You're going to need to come up with the illid, so how you're making the illid, and of course you're going to need the carbonyl. So think about it, and then we will discuss when we meet on Thursday.